Hello, everyone. So our next speaker is Nicholas. Actually, Nicholas is actually coming from Rice University. His topic is about the RSH-based MPI system for billion-scale similarity search. Let's welcome him.
Yeah, so as he said, we're talking about doing similarity search and like billion-scale data sets. Our algorithm is based on locality-sensitive hashing, and it is distributed using MPI. So let's just start by talking about the problem we're trying to address. We're interested in the k-nearest neighbors problem, or KNN, which is for a given data set, a given distance function, and a given query vector. We want to find the k vectors within the data set that have the closest overall distance to the given query vector. So you can see here, in like a 2D form, it's a pretty simple problem. But our interest is in like ultra high dimensionality data sets, so where you have vectors that have like 1,000,000 dimensions or more. This has a wide variety of applications in terms of like fraud and spam detection, looking at fraudulent emails and comparing them to a new email to check its legitimacy, behavior prediction, so like ad clicks, consumer preferences. Genomics is a huge application, doing sequence matching and trying to find matching DNA sequences, and then also in text search and recommendation. Google search and tools like that are great for short queries, but if you wanted to compare an entire article and search for other similar articles, they're not as ideal. So how do we do distributed near-neighbor search efficiently? So the first thing we do is we're not doing exact near-neighbor search. We're talking about approximate near-neighbor search, which for a wide variety of applications, like especially recommendations and genome sequencing, is sufficient. And this allows us to use a technique called locality-sensitive hashing and combined with other sketching and algorithmic techniques to generate a very fast and scalable system. We were able to test our data set using 1 billion vectors from the Criteo click-through data set. Each of these vectors is about 1,000,000 features sparse, and then we were looking at computing a batch of 10,000 queries on this. Using a standard KNN, this would require at least 10 trillion vector multiplications, which is prohibitively expensive. But using our system, we could completely index this data set in about 2,000 seconds. Most of this is just the time spent reading to disk. And then we could compute this batch of 10,000 queries in around 2 seconds. So we compared our system to PySpark, which is a MapReduce system based on the Spark framework. Allows you to split data across nodes in a compute cluster, process them in parallel, and then aggregate the result. And so if we compare ours, this is using about a gigabyte-sized data set and computing a batch of 100 queries. We can see that with PySpark, it took about 4 to 8 minutes to compute that batch of queries. On our system, it took a little under 1/10 of a second. We can look at the average cosine similarity as a means of evaluating these two systems. We can see that the random similarity for this data set is 0.33, and both ours and PySpark were about the same. So you're not paying, using our system, you're not paying any cost for that additional speedup. So how do we build this? So let's start off talking about hashing real quickly, just to get a general definition. So a hash function we can define as any mapping from any variable-sized input to any fixed-sized output. So you could map every vector in R10 to an integer between 0 and 100. So what we're interested in is a special class of hash functions called locality-sensitive hash functions. And locality-sensitive hash functions are unique by the property that the probability that two vectors have the same hash, or that their hashes collide, is directly proportional to the similarity between those two vectors. So if you look at a data set, if two vectors have the same hash, that means that those vectors are likely very similar. A classic example of locality-sensitive hashing is minwise hashing, or minhash. And this is done by considering a binary vector, going through and computing the hash of the indices of all the non-zero elements, and simply taking the minimum value of all of those hashes. So how can we do similarity search with this? So it works in 2 phases. The first phase is the indexing phase. We take our data, we construct L hash tables, and each hash table has an associated locality-sensitive hash function. We go through our data set, and we compute a hash on every vector in it with every one of the hash functions, and use that hash value to store it in that hash table. Then, when we want to query it, we can compute the hashes of the query vector to look at those hash buckets in the hash tables, and then consider only the subset of the data set that's contained there. And this works because based on the properties of locality-sensitive hashing, we know that the vectors in these buckets had a similar hash to the query and are therefore more similar. So this allows us to, in one simple step, reduce the search space from the entire data set to just the small subset that's contained within those within those hash buckets. So then the first thing we can do is how can we improve this process? And the first thing we can do is look at the hashing cost. So min hash, like we talked about earlier, requires a full pass-through with a vector for every hash computation. And when the number of hash tables you're using increases and the size of each vector increases, this adds a lot of overhead to the process. So we can simplify this by using something called densified one permutation hashing, or DOPH. And DOPH allows us to compute as many hashes as we want on a given vector in a single pass through it. And the way this works is you consider the range of the hash function, and if you want to compute k hashes, you bucket that range into k partitions, and then as you pass through the vector, you, instead of storing the overall minimum hash like you would for general min hash, you consider the minimum hash in each of the partitions. And thus, in one pass through, you have all the hashes you need. And this changes the cost of, this transforms the cost from the cost of computing hashes to just the cost from reading the vectors to disk, which is the new bottleneck. The next thing we can do is eliminate the overcrowded buckets in the hash table. So one of the problems with this is you have the case where a large number of vectors all get hashed to the same bucket in the hash table. And so you get a huge exploding bucket that requires you to keep allocating new memory and also costs more at query time because you have to consider all of those vectors. What we can do is replace each of these buckets that is variable sized with a fixed size reservoir and insert elements into it using the reservoir sampling algorithm. Which works as follows. While the reservoir is still empty, you can just insert the elements into it. But once it's full, you choose a random number. And with equal probability, you either replace one of the numbers that's already in one of the elements that's already in the reservoir, or you discard the new element. And this works because if you consider our application where you have a set of L hash tables, it's unlikely that a vector will get hashed to an overcrowded bucket in every single one of those hash tables. And if it does, that's emblematic that the vector is already, the contents of that vector are already represented by vectors you've already seen in the data set. And so if it gets discarded, it doesn't decrease the overall accuracy. And then the final improvement we can make is faster top K selection. If we reflect back on the fact that locality-sensitive hashing guarantees that similar vectors are more likely to have the same hash, then if a given vector in the data set is very similar to your query vector, it will collide with the query vector in more hash tables. And so instead of simply doing like a brute force KNN once we've extracted the reservoirs from the hash tables, we can actually just count the frequency that different elements occur within those reservoirs, and whichever elements occur the most frequently are therefore the ones that were most similar to the query. So we can see here we can take the vectors, if those are the reservoirs we sample from the hash tables, and we can do frequency counting, and it will read the most frequent elements are the ones that we're returning as our top K nearest neighbors. So we have that, and that works great on single machines. It's incredibly fast. But how can we do it in a distributed setting? So there's several considerations. The first is that we want to be able to divide the memory load across all the nodes in the cluster. We don't want to have to we don't have to process the entire data set in every node. We want to be able to fragment it, and so we can increase the parallelism and increase the speed. And the second thing we need to be aware of is we want to be able to, once we have the results, we need to be able to aggregate it quickly from all the nodes in the cluster in order to get fast query times. So let's talk about that second part. How do we aggregate the results of sampling the reservoirs in L hash tables on n different compute nodes incredibly efficiently? And we can do that using sketching. The naive way of doing it would be to take all of the reservoirs from all the nodes in the cluster and copy them to one central node, and we can do whatever similarity search or frequency counting we want to there. However, that's very slow and requires a lot of memory transfer. So we can construct a sketch using the reservoirs we sample from every node that is much more efficient to transfer and that can still preserve the property of we can easily determine which elements occurred most frequently. And so we use something called TOPKAPI, which is a NeurIPS paper from 2019. And it had several important properties. One, it's streamable. Once we construct the sketch, we can easily pass more and more. We can sample the reservoirs from the hash table and easily add the elements to it. The next one, and this is very important, is it's mergeable. That means that if we have two sketches, for example, the sketches from two different compute nodes, we can combine them into one single sketch with one linear pass through. So it's incredibly fast. The next thing is this sketch allows us to quickly, it's an estimation of the frequency occurrences of different elements. And so it allows us to very quickly, from the sketch, determine which elements occurred most frequently in the data stream that we use to construct the sketch. And then finally, it's compressed. It's very space efficient, and so we can easily transfer them between different nodes and merge them. And so how our system works. To start out, so we take our data set, represented by the top, and we have n compute nodes, and so we construct a set of L hash tables in each of the compute nodes. We then index and store all of each partition of vectors into the hash tables in that particular compute node. And then that's it. And that can be done completely in parallel. And so we get linear speedups with respect to the fraction of the data that's in each node. So when you double the size of the cluster, it halves the indexing time. So that's good. And then to query it, we can take a batch of query vectors, and we can do queries in batches to increase the parallelism. And we can compute the hash of those query vectors in parallel using the cluster. We can aggregate those query hashes, distribute them to all the nodes, and then sample the reservoirs corresponding to those query hashes. Once we have those reservoirs, we can construct a sketch using each of those reservoirs in each of the nodes. And now the question is, how do we aggregate these results into one final set of nearest neighbors for each query? So we have 3 different methods we looked at for that. The first is we can do, as a benchmark, is saying, let's not use sketching. Let's just take all these reservoirs we sampled, copy them to one central node, and then do exact frequency counting there. The next is, let's use a sketch. So let's construct a sketch in each node, copy all of those sketches to one central node, and then merge them and compute the final top k nearest neighbors. And then the final method we tested is using sketches again, only this way using them in a custom MPI reduce function we wrote that will aggregate them in parallel using a tree form, and then ultimately get one final merged sketch. So what this looks like is, this is the first one. We can just copy the reservoirs from every node to one node, do exact frequency counting, and get our nearest neighbors. We can do this better. We can construct sketches, do the same thing where we copy all the sketches to one node, and then get our final merged sketch and nearest neighbors. And then we can do this. And this is, we construct a sketch in each node, and then we merge the sketches by passing them to the left until we reach one final merged sketch. And thus, the number of steps and the number of communications is log n with respect to the size of the cluster, and then times the cost of merging the sketches, which we already established is linear. So that's very fast and very efficient. So this brings us back to how we were able to do billion scale similarity search. We can take this huge data set, and we can chunk it up across a cluster. We were only using a compute cluster with 10 compute nodes, each with around 4 cores. And we were able to do all of this in minutes. So this took around 30 minutes to do the entire setup and 2 seconds for the queries. So very fast. If we look at the indexing time of this system, this is on the KDD12 data set, which is around 150 million vectors, each with 1 million features. As we increase the number of nodes, we can see that the indexing time goes down. And then if we look at our query time, we have our 3 different methods we looked at. The one at the top in green is the exact frequency counting, where we copied all the reservoirs. We can see it scales fairly poorly. We start using sketches, and it goes down significantly. And then if you see the blue graph at the bottom, that shows using sketches and our tree-based aggregation pattern. And so we can see here that as we increase the size of the cluster, it scales logarithmically. We can even go all the way up to a cluster of 30 compute nodes, and it will still remain relatively unchanged from the initial query time. We can evaluate the similarity of each of these 3 methods, and we see that exact frequency counting gets us a slightly higher similarity, but it's not significant. So at the top, 0.83 versus 0.85, and then here, about 0.72 versus 0.76. So it's about the same, and this is again looking at the average cosine distance between the query vector and the vectors we returned. And then just for another point of comparison, this is using a web spam data set, and this is all 3 of our methods, again, compared to the ground truth. So the theoretical highest degree of similarity you could get for the data set using exact similarity search is around 0.97. Using our system, we can get just 0.9, and you could change this even more by messing with hyperparameters. It'll just be slightly slower. So to wrap it up, so basically we can do large-scale similarity search using approximate methods, and we can get vectors that are very close to the given query vector, only in a fraction of the time, and with far less resources. Yeah.
Any question from the speaker?
You mentioned the cost of indexing. Is this all one-shot indexing? Does the system allow incremental indexing or adding more elements? And what's the cost associated with that?
You mean like if you want to add more elements to the tables? Yeah, so our system, I guess I shouldn't touch on this. So our system supports two ways of doing this. One, you can just give it an input file, and it'll automatically partition it and do all the indexing in parallel. You can also give it a set of input files, and each compute node will just be responsible for one. You can continually do that. You could add a bunch of data. You could compute queries. Then you could add more data, compute more queries. Totally fine.
Any further question for the speaker? Well, if not, let's find our speaker again.